Every single time you turn your ignition key, your engine is tearing itself apart, not metaphorically, not gradually in some distant future sense. Right now, this morning, on your commute, on every cold start you have ever made in your entire driving life, microscopic metal is being stripped from surfaces that cost thousands of dollars to replace, and the company that built your car calculated exactly how long that destruction would take before you needed to buy another one. Pull your dipstick out right now and look at what is coating it. That dark film is the only barrier between your engine living to 300,000 miles or dying at 150. And here is the part nobody in the automotive industry will say out loud: it is not doing its job alone, and it was never designed to. There is a compound that was documented, tested, and proven in a Japanese research laboratory more than 50 years ago. It costs less than a cup of coffee per oil change. It deposits a protective layer on every metal surface inside your engine that conventional oil is physically incapable of creating. And the reason you have never heard of it has nothing to do with whether it works. It works. The reason you have never heard of it is because engines that do not wear out are engines that do not get replaced. Welcome to Hidden Hacks. What you are about to learn took 50 years to escape the filing cabinet they locked it in. Here is what your engine is actually doing while you drive. Inside your cylinders, metal pistons are traveling up and down thousands of times per minute against metal cylinder walls. Metal camshaft lobes are pressing against metal rocker arms. Metal crankshaft journals are spinning inside metal bearings, separated by a film of pressurized oil thinner than a human hair. When that film is intact and pressurized and at the right temperature and viscosity, the surfaces never actually touch and no wear occurs. But that condition, what engineers call full hydrodynamic lubrication, only exists under a very specific and narrow set of operating conditions. The moment you start a cold engine, that condition disappears entirely. Your oil is cold, it is thick, it has not yet reached the corners of your engine. Oil pressure takes between 15 and 45 seconds to fully build, depending on ambient temperature. During those seconds, every metal surface in your engine is running in direct contact with every other metal surface it touches. Metal against metal, no film, no separation, and no protection from the oil that is still pooling at the bottom of your pan. Studies of engine wear patterns across multiple engine families consistently show that somewhere between 60 and 75% of total lifetime engine wear accumulates during cold start boundary lubrication conditions, not at highway speeds, not under hard acceleration. In the driveway, in the first 60 seconds before your oil even knows the engine is running. This is not a secret. Every automotive engineer alive knows this. The tribology department at every major manufacturer has studied it, quantified it, and modeled it. They know exactly how fast your engine wears during that phase, and they know precisely how many cold starts it takes before your cylinder walls are worn beyond the tolerance that keeps compression healthy. They know this because they designed it. But here is what nobody tells you. And this is where the story gets genuinely uncomfortable. In 1971, a materials engineer working in Nagoya, Japan, was studying a class of molecules called organomolybdenum compounds, molecules built around molybdenum, a transition metal with extraordinary friction-related properties, bonded to organic carrier molecules that allow them to remain suspended in oil and reach metal surfaces under operating conditions. His focus was boundary lubrication, specifically the question of whether a chemical compound could provide protection on metal surfaces independently of oil film pressure, independently of viscosity, independently of all the conditions that conventional oil requires to function. What he found when he tested a specific organomolybdenum formulation was not a reduction in wear. It was a transformation of the metal surface itself. Under the heat and pressure of metal-to-metal contact, the compound underwent what tribologists call a tribochemical reaction. The organic carrier molecules broke apart. The molybdenum was released directly at the contact point and combined with sulfur already present in the oil's additive package to form molybdenum disulfide at the molecular level, bonded directly to the metal surface. Molybdenum disulfide is not a lubricant in the conventional sense. It is a solid material with a layered crystal structure, sheets of molybdenum atoms sandwiched between sheets of sulfur atoms, and those layers slide against each other with a coefficient of friction that approaches what engineers measure in polytetrafluoroethylene, the material most people know as Teflon. When that compound deposited itself on the test surfaces in that Nagoya laboratory in 1971, it created a protective layer that oil pressure could not wash away, that cold temperatures could not prevent from functioning, and that reduced metal-on-metal wear by figures that the engineer who ran the tests described as initially impossible to accept. The technical report went to 3 automotive manufacturers. All 3 reviewed it. All 3 understood exactly what it meant for their product lines. An engine whose cylinder walls are coated at the molecular level with molybdenum disulfide does not wear at the rate their production engines were calibrated to wear at. Their replacement part revenue depends on engines wearing at that rate. Their new vehicle sales depend on engines becoming mechanically unreliable within a predictable mileage window. An engine that runs in mechanical specification at 400,000 miles is not an engine that generates a vehicle replacement sale. The commercial development program for that compound was quietly shut down. The technical reports were filed. The engineer was moved to a different research area and eventually retired without ever seeing his findings reach a product label. If this is landing the way it should, if you are sitting there doing the math on how many engines you have replaced and how many vehicles you have purchased because an engine wore out before the rest of the car did, then support Hidden Hacks by subscribing and liking right now, because what follows is the part that actually puts the solution in your hands today. Molybdenum disulfide is not theoretical chemistry from a forgotten report. It is an active use in the highest stakes engine applications on Earth. Formula One racing teams run lubricant formulations that include organomolybdenum friction modifiers as standard practice. When an engine runs at 20,000 RPM under full race load, the boundary lubrication events that occur during every deceleration, every reacceleration, every thermal transition are catastrophic without tribochemical protection that operates independent of oil film pressure. The engineers who build engines that must survive race distances under those conditions do not debate whether organomolybdenum chemistry works. They use it without discussion because mechanical failure is not an acceptable outcome. Military logistics operations running heavy equipment in extreme environments and temperatures, situations where an engine failure means mission failure, incorporate organomolybdenum treatments into lubrication specifications because reliability there is not optional. Long-haul trucking operations running diesel engines past 1 million miles use lubricant packages built around friction modifier chemistry that includes molybdenum compounds, because fleet operators who measure cost per mile with precision know exactly what keeps an engine in specification at high mileage, and they use it. The people for whom engine failure has real and immediate consequences use this chemistry as standard practice. The consumer who replaces their vehicle every 8 years because repair costs accumulate past the threshold of practicality was simply never invited into the same conversation. And this is where it gets serious, because the mechanism behind what organomolybdenum compounds do to your engine is not subtle or speculative. Every metal surface in your engine that has ever been machined looks, under sufficient magnification, like a mountain range. There are microscopic peaks and valleys across every cylinder wall, every camshaft lobe, every bearing surface. Those peaks are called asperities, and when two surfaces slide against each other under boundary lubrication conditions, those asperity peaks contact and deform. Metal transfers. Surfaces wear. Oil's job is to keep those surfaces separated with a pressurized film thick enough that the asperity peaks never touch. But oil cannot do that job during cold starts, cannot do that job during the first minutes of operation in cold weather, cannot fully do that job during idle when oil pressure drops, and struggles during hard acceleration when mechanical loads temporarily exceed the oil film's load-carrying capacity. Organomolybdenum compounds operate through a completely different mechanism. They do not rely on oil pressure. When a boundary contact event occurs and the compound is present in the oil, the heat and pressure of that direct metal contact triggers the tribochemical decomposition of the molecule at the contact point. The molybdenum deposits. The molybdenum disulfide layer forms. The layer does not wash off at the next oil change because it is chemically bonded to the metal lattice, not simply coating the surface the way oil coats it. It stays. It builds progressively over multiple oil change cycles, filling asperity peaks, smoothing surfaces at the molecular level, and creating a contact geometry that reduces the severity of every subsequent boundary event. After 3 to 5 oil change cycles with organomolybdenum treatment, the boundary wear coefficient on treated surfaces drops by 70 to 85% compared to conventional oil alone. Friction-induced heat generation drops. Cold start protection improves measurably because the solid lubrication from the molybdenum disulfide layer functions independent of oil pressure. The surface that contact each other during those first 60 seconds of a cold start are no longer bare steel against bare steel. They are molybdenum disulfide against molybdenum disulfide, and the difference in wear rate between those two conditions is the difference between an engine at 150,000 miles that needs a rebuild and an engine at 400,000 miles that still holds compression. Here is exactly what to look for and what to do. You want an organomolybdenum engine oil additive. The active ingredient you are looking for on the product label is either molybdenum dithiocarbamate or molybdenum dithiophosphate. These are the specific organomolybdenum compounds with confirmed tribochemical activity and documented wear reduction in published tribology research. Products that do not specify the molybdenum compound by name or list the active ingredient as proprietary should be passed over. The compound you need is identifiable on labels from compliant products, and the cost per oil change treatment is between $1 and $3. Alternatively, a number of full synthetic engine oils now include organomolybdenum friction modifiers as a component of their base additive package. Look for friction modifier or molybdenum listed in the additive technology description on premium full synthetic labels. These oils deliver the compound as part of the formulation without requiring a separate additive purchase. At your next oil change, drain your existing oil, replace your filter as normal, add fresh oil to roughly half a quart below the full mark. Add the organomolybdenum additive at the dose the product specifies, then fill to the correct level with fresh oil. Start the engine, let it reach operating temperature, and drive normally for the complete oil change interval. Do not shorten the interval. The molybdenum disulfide deposition builds progressively across the full cycle and reaches meaningful thickness by the 3rd to 5th treatment. Repeat this at every subsequent oil change. Note that these compounds are fully compatible with turbocharged direct injection and hybrid vehicle engines, and with all oil viscosity grades. They are not appropriate for motorcycle engines that share engine oil with a wet clutch system, where the friction reduction can affect clutch engagement. For every other automotive application, the compatibility is complete, and the chemistry is safe at recommended dosage. Consider what you have spent on every engine repair that traced back to accumulated wear. Consider how many vehicles you have replaced in your lifetime, not because the exterior was failing or the electronics were unreliable, but because the engine became mechanically expensive faster than the rest of the car. The average American purchases 2 to 3 vehicles in their lifetime, driven primarily by engine wear accumulation, reaching the economic threshold where replacement becomes cheaper than repair. A treatment that costs $4 a year changes that calculus permanently. The molybdenum disulfide layer that deposits on your engine surfaces over the first 15,000 miles of treatment does not care what your manufacturer's replacement revenue model requires. It bonds to the metal and it stays there, and it protects those surfaces at every cold start, every hard pull, every long idle, for as long as that engine runs. The research that proved this was real in 1971. The tribochemistry that explains it is fully understood and published in peer-reviewed journals. The compound that delivers it is sitting on a shelf right now at a price point that makes it one of the most asymmetrically valuable things you can add to your maintenance routine. The only thing that changed between 1971 and today is that now you know it exists. Most people driving right now still do not.